Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Xingjian Zhang from University of Hong Kong. So he will give us a talk on this quantum magic advantage in shallow circuit computation. About our speaker for today. So he is a postdoc at the Department of Computer Science at the University of Hong Kong. He got his PhD in Tsinghua University under the supervision of Xiaofeng Ma. And his main interests are in problems in quantum non-locality, quantum communication, and quantum cryptography. And he has papers published in journals such as PRL and PRX Quantum and so on. And he also has work on research on device-independent quantum information, and is a participant in a focus group of the standardization of quantum information technology from networks. So, okay, the floor is yours, Xingjian.
Thank you for the introduction. And I'm Zhang Xingjian from the University of Hong Kong. And it is my pleasure here to introduce our results on unconditional quantum magic advantage in shallow circuit computation. And first, I would like to thank my collaborators, Mr. Zhao Kaipan and Guoding Liu from Tsinghua University. Okay, my talk will be organized as follows. First, I will introduce the background and motivation, and then I will introduce the main topics for this work, shallow circuits and quantum magic. So at a high level, we transform the shallow circuit problem into the study of a special form of quantum nonlocality, namely quantum pseudo-telepathy, where we found that quantum magic plays a non-trivial role. And for the construction, we take advantage of the linear binary constraint system, linear BCS. And in the end, I will take an outlook. Okay. So ever since Richard Feynman proposed the idea of quantum computation, we have the strong belief that quantum theory brings us means to solve certain problems faster than any classical counterparts. So Feynman's idea comes from the straightforward physical intuition that in quantum theory, we have a state space that is exponentially larger than that in classical physics, in Newtonian physics. So the state superposition brings us a means to conduct a parallel computation. So this should bring some means of should bring us some sort of speed ups. But despite this straightforward physical intuition, mathematically, we still need to answer the following questions rigorously. Does quantum theory indeed bring us a computational advantage? And if yes, what is the origin of such an advantage? So renowned result that seems to respond to both questions is the Gottesman-Knill Theorem. So this theorem actually starts from an opposite question. How well can classical circuits simulate quantum ones? Gottesman and Knill found that there is a class of quantum circuits which they name stabilizer circuits. No matter how deep these circuits are, they can always be classically simulated within a polynomial time of the input size. So for a stabilizer circuit, the physical state is first initialized in 0, or a computational basis state. Then this state undergoes a series of unitary operations which are restricted to the Clifford gate. Here, a Clifford gate means it is an operator that matches a polystring operator into some polystring operator. So it is the stabilizer group of the poly group. And finally, the state is measured on the poly basis to generate the final computational result. So since these circuits are quite restricted, they do not realize universal quantum computation, and there are some quantum states that are beyond the reach of stabilizer circuits. So we term such states magic states. So they cannot be prepared at any intermediate stage of a stabilizer circuit. Here I present two examples in the qubit case. So one is the T state and another is the H state with the density operators given as follows. So to realize universal quantum computation, we must resort to some resources that go beyond the stabilizer circuits. And one way to realize universal quantum computation is by magic injection. In this formalism, the operations are still restricted to the stabilizer operations. So you still apply Clifford gates and polymorphs. But at first, instead of initializing the physical states on the computational basis state, we inject some magic states. So some magic states like the H state and T states we have just seen. We inject some magic states into the circuit to realize the general computation. Well, another way is more like a standard circuit model, and this is actually the formalism we consider in our work. The initial state is still the zero state or the computational basis state, and the final measurements are still the Pauli measurements. But in the middle, instead of applying just Clifford gates, we apply a universal gate set. There are many examples of a universal gate set. For example, the quantum control NOT gate plus all single qubit gates, or a control NOT gate plus a Hartmann gate plus a T gate, or in some sense, a minimal gate set, a top gate plus a Hartmann gate. Well, in all these examples, we need at least one non-Clifford gate, such as the T gate, which adds a non-trivial phase parameter to the computational basis state superposition, or the Toffoli gate, which is a 3-qubit quantum gate that can be seen as a quantum generalization of the NAND gate. And if we inspect the well-known quantum algorithms, such as the Schur's algorithm for factorization or Gover's search algorithm, we shall find that these algorithms exploit many non-Clifford gates or equivalently the magic states for the realization. We believe that this algorithm brings us some quantum advantage, but do we have an unconditional proof of such an advantage? Unfortunately, we do not have such a proof. So in Schur's algorithm, we actually assume the factorization problem is classically hard, yet we do not know how to prove it. And in Gover's search algorithm, the advantage is in the sense of query capacity. That means that we have an oracle, and for a quantum machine and a classical machine, they can take queries to the oracle, and it can be proved that the quantum machine takes fewer queries to realize this search problem. But if we want to consider the standard Turing machine model and we build this oracle with gates and quantum states, then it becomes problematic whether this global search algorithm indeed brings us a quantum advantage in the gate complexity regime. So to firmly establish an unconditional quantum advantage, let us first re-examine the definition. In the previous discussions, we deemed the polynomial time computation as efficient. In this fashion, to manifest a computational advantage, we need to find a task where a quantum machine runs super polynomially faster than any classical ones. And in the language of complexity theory, this means that BPP is not equal to BQP. And as we have discussed, this is hard to prove. But now, what about considering a more restricted regime where we consider a computational time smaller than polynomial as efficient? Well, besides being possibly easier, an important motivation is that an advantage in this fashion is somehow a necessary condition for an advantage in a deeper circuit regime. And in complexity theory, we have the experience of hierarchy classes. So some low complexity classes become identical, such as the polynomial hierarchy class and the pegging argument. And a notable low complexity regime that we will discuss later is the shadow circuit, where we take a constant computational time, namely a constant circuit depth, as efficient. And typical classes in this regime include NC0, AC0, and their quantum counterparts. In our work, we shall focus on the NC0 type classes, and later I will present their definition. Shadow circuit computation was partially initiated from an experimental perspective, as they are easier to handle with for the NISC or early fault tolerance devices. And moreover, theoretically, we have more tools for their analysis. Okay, for the discussion of shadow circuits, we first review some basic notions. So the first notion is the gate fan-in, which is the number of classical bits or quantum bits a gate can act on at a time. So for example, for the classical logical gate, the AND gate and the quantum control NOT gate, they both have fan-in too. And in our work, we account for both the classical bits and qubits for the calculation of gate fan-in. So in this fashion, we can unify the discussion for the classical logical gates, the unitary operations, the quantum gates, or the classically controlled quantum gate, and also the quantum environments. So we can see what is the gate fan-in of all these operations. And another concept, actually, we have mentioned several times, is the circuit depth, which is the number of steps to execute all the gates in the circuit. So it is the longest path in the circuit. And in this example, the circuit depth is 3 because we have a longest path of, say, the first XOR gate, then an AND gate, and finally another XOR gate before we read out the computational result. Okay, based on these notions, we now define the circuit classes NC0 and quantum NC0 circuits. In these circuits, all the gates have a bounded fan-in, namely, each gate can act on at most some constant number of input bits or qubits. Also, these circuits have a constant circuit depth, which we term shallow. These two features have some clear physical interpretation. The bounded fan-in can be seen as a flat speed for information transmission within this circuit, and the constant circuit depth can be seen as a scrambling time for a constant time for information scrambling. And these features remind us of another concept in quantum theory, which is quantum nonlocality. As we all know, the Bell theorem tells us that there can be some spooky action at a distance. So imagine there are two distant non-communicating observers who perform random quantum environments on their system. And these general random quantum environments can generate some correlated statistics which are purely quantum. And if these observers do not share a quantum state or do not make quantum environments, which we call they are classical observers, then they must resort to communication to simulate such quantum statistics. And in the language of computer science, we can describe this Bell test scenario as a synchronous game. So in a synchronous game, the non-local observers are now called non-local players. They do not communicate with each other once this game starts. And in the game, there is a referee who picks up 10 questions, which responds to the environment settings in the Bell test. And the referee asks the two players to generate answers with respect to the questions. We say these observers, these non-local players win the game if and only if their output answers satisfy a certain relation with respect to the input questions. So we can write it as a function where the function equals to 0. We know that the quantum theory brings these non-local players with some strategies that can outperform classical strategies. And in certain cases, these quantum players can even win this game perfectly. So this is a phenomenon we term quantum pseudo-telepathy. And naturally, they must use some entangled state, and they must take some synchronous quantum environments to generate such perfect answers. And by using this phenomenon of quantum pseudo-telepathy, we can construct some relation or search problems that separates the NC0 circuits and quantum NC0 circuits. A relation problem is that the circuit output, the output which we denote as O, it needs to satisfy a certain relation with respect to the random inputs to the circuit. So the input we denote as I. So this is very similar to the definition of a synchronous game. So there is a systematic way to transform a synchronous game into a relation problem by embedding this quantum pseudo-telepathy game between randomly chosen computational sets. So you can imagine that there are two randomly chosen computational sets, which we label as I and J. They are input with the questions in the synchronous game alpha and beta, and they are requested to generate the desired answers in the synchronous game. Another way of interpreting this relation problem is to describe it as an input conditional sampling of nonlocal statistics. So a natural way, so as you can imagine, if there is a phenomenon of quantum pseudo-telepathy, by embedding this strategy in the circuit, we can solve this relation problem within a shadow circuit. But if the circuit is the circuit does not have some quantum power, or that it cannot win this synchronous game, then it requires an O2O communication between all the computational sites to perform this relation problem. And an O2O communication requires at least a log n depth, where n is the input size, this log n depth circuit. And this is beyond a beyond a shadow circuit. So in this case, a shadow circuit is incompetent for solving this task. Okay, so by embedding this logic to some well-known results in the literature, to some well-known synchronous game, people have shown a separation between the NC0 classes and quantum NC0 classes. Nevertheless, if we take a further inspection on this result, we shall find that this separation is actually between classical circuits and Clifford circuits. So such an advantage is an unconditional Clifford quantum advantage. Now you may wonder, what is the role of quantum magic in the shadow circuit regime? So intuitively, should you believe that BPP is not equal to BQP, you may expect that the magic shall bring an unconditional quantum advantage in the shadow circuit regime as well. And from a practical perspective, if we can show an unconditional magic advantage, then we may come up with some more exotic experiments that can be performed on the NISQ or early fault tolerant platforms. Okay, so if there is a quantum magic advantage in the shadow circuit region, here I depict a conceptual diagram showing the fine structure made by magic. So in the first level, the NC0 circuits, the gates are restricted to classical logical gates. Correspondingly, in the synchronous game, the players are restricted to shared randomness and classical operations. And at the second level, the Clifford NC0 circuits, we can use general Clifford gates and polymeroments. And this corresponds to a Clifford strategy in playing a nonlocal game, where the players can use a stabilizer in tangled state and local Clifford operations. And finally, in a generic quantum NC0 circuits, all types of bounded fine-in quantum operations are allowed. And the corresponding quantum strategy in the synchronous game allows the players to share general quantum entanglement, and they can perform general local quantum operations. A super constant circuit depth separation means that there is a nonlocal game where, with more exotic quantum resources, the game can be won perfectly. Otherwise, there is a strict upper bound on the winning probability. And our main result is that we find such a game where we can separate the Clifford NC0 circuits and quantum NC0 circuits. The main ingredient is that there is a family of nonlocal games such that under proper parameters, this game can be either won perfectly by classical strategies or only by Clifford strategies, or you must resort to some general quantum resources that use non-Clifford gates or magic states. Okay, now let's go into some detail. Our method starts from the linear binary constraint system, linear BCS. So here, a BCS means a set of Boolean functions over the binary variables in Z2. So Z2 can be either 0 and 1 or plus and minus 1. And for later convenience, we shall use the standard variables plus and minus 1. So for example, the 3 set is BCS. And in addition, we require that each constraint is linear in its composing variables. And for the set variables, it means that the product of a set of variables is equal to +1 or -1, equal to the constraint. This definition is over classical variables, and we can generalize the concept into the operator value regime, or which we call a quantum generalization. In this case, the classical variables are replaced with finite dimensional Hermitian operators with eigenvalues +1 and -1. and the constraints become the plus or minus identity of corresponding dimension. Note that in this generalization, we do not restrict the dimension of the Hermitian operators, so they can be some arbitrarily high dimension. The reason we say this is a quantum realization is we can somehow realize this BCS via quantum measurements. So we measure we take the quantum measurements of the Hermitian operators on some state, and the measurement results, which are classical values of +1 or -1. The measurement results shall satisfy the BCS constraints in a classical fashion. Now you may notice that we need to take some joint measurements on the same state to realize one constraint. So this poses an additional requirement that in each constraint, the corresponding Hermitian operators, they need to be compatible measurements so that we can take a joint measurement of these operators. A useful way to understand a BCS is to regard this description as a group representation. So in this group presentation, the constraint +1 corresponds to the identity element in this group, and the -1 constraint corresponds to some element in the group, which we denote as J. In the literature, it has been proved that to solve this BCS is equivalent to solving the representation of the group, and the existence of a non-trivial solution to the BCS is equivalent to that. In this representation, this J element is not equal to the identity element. Since we do not restrict the system dimension, this problem is in general an undecidable problem. But as we shall later see, in some specific cases, the problem can be decidable or even efficiently solvable. Okay, now we have some examples to give you some sense. A famous linear binary constraint system is the Mermin-Pierre system, and in the literature, it is also called a magic square. Well, amusingly, the magic square does not use magic states, so we shall avoid this terminology to avoid confusion. So the left figure shows this Mermin-Pierre system, and each row or each column corresponds to a constraint. And each single line means that the product of the three variables equals to +1, or the plus identity, and the double line means that the product of these three variables equals to -1. You can easily check that this system does not have a solution over Z2. It does not have a classical solution. So you can either apply methods like Gaussian elimination or the variable substitution to check this. On the other hand, this system has a quantum solution. So on the right-hand side, at least one such solution. Now we have defined what is a BCS. The next step is that we can translate a BCS into a synchronous game. So this translation is quite straightforward. So in this game, the referee picks up a constraint labeled by CJ and a variable VI within this constraint. The referee asks Alice to give a satisfying assignment to this constraint. So Alice's goal is to fill in all the variables within this constraint. And for Bob needs to output a value for this variable VI. The two players win this game if and only if Alice gives a satisfying assignment to CJ, and both players give equal assignments to this same variable VI. And as you can imagine, the existence of a perfect winning strategy in this synchronous game is equivalent to this BCS having an operator value solution. And the existence of a classical strategy is equivalent to finding a classical solution to the BCS. In the quantum case, suppose this BCS has a operator value solution given by a set of information operators AI. Then Alice and Bob can first share a maximally entangled state of some proper dimension. Then Alice measures these Hermitian operators of the BCS solution, and Bob measures the transpose of these operators. Since these operators give satisfying assignments to the BCS, the Alice's assignment naturally satisfies each constraint she receives. And furthermore, we utilize this property of the maximally entangled state, and Alice and Bob always give the same assignments to the same variable. And in summary, the existence of a perfect winning classical strategy in the synchronous game is equivalent to finding a classical solution to the BCS, or which means that we solve this BCS over the group Z2 over the upper group. And the existence of a Clifford strategy is equivalent to this BCS has a solution over the poly group. And in general, the existence of a general quantum strategy is equivalent to solving this BCS over some finite group. And you may wonder that if this BCS does not have a solution, whether Alice and Bob can somehow win this game very close to the perfect winning. And this has been disproved. So if the BCS does not have a solution, then either Alice fails to give some satisfying assignment to one of the constraints, or that the players send different values to some variables in the game. And for either case, you can upper bound the winning probability of the players in a synchronous game. By using this BCS-based synchronous game, so we can we show that the Mermin-Pierre system has a separation between the Clifford strategy and polystring or the polystring strategies. And using the Mermin-Pierre system, we can separate the NC0 circuits and NC0 circuits. And to use such a Mermin-Pierre system, we know that we can efficiently solve the system over Z2 to check that it does not have a classical solution. And in the literature, we know how to construct a polystring solution to the system. So we can construct some Clifford strategy to play the synchronous game. Now we want to separate Clifford NC0 and general quantum NC0 circuits. And the target is now transformed to finding a new linear BCS, which does not have a polystring solution, but it has some general quantum solution that requires non-Clifford gates. Now the problem is twofold. So how do we solve a linear BCS over the poly group to check that it does not have a polystring solution? And second, where do we find such a linear BCS which has a non-Clifford solution? So our main result is that we indeed find a linear BCS which has some non-Clifford solutions but does not have any polystring solution. So this construction is it is hard to say how we find this BCS. It comes from Eureka times. And if you are interested, I can show the construction later. Well, if you do not like this construction, there is some systematic way to finding potential linear BCS having the BCS properties. So in a recent work by William Slostra, he proposed a group embedding technique. So you start with a group presentation, a group you like, and you write this presentation in some proper way. As you remember, BCS can be seen as a presentation of some group. So there shall be some links. So in this first step, this group presentation may not be in the fashion of a linear BCS. So you take some embedding procedures and enlarge this group. And finally, you will arrive at a linear BCS presentation. So those trust results guarantee you that this final linear BCS has at least one non-trivial operator value solution which respects the original group, so the underlying group you consider. So now you have a non-trivial linear BCS which has some quantum solution. But the problem is that this procedure does not guarantee you this linear BCS does not have a polystring solution. So you still need to check whether this BCS has some polystring solution or not. So for this problem, we have another result. We construct an efficient classical algorithm which can check a general linear BCS has a polystring solution or not. And if it has a polystring solution, then this algorithm can output one such solution. And for the rest of the time, I will introduce this algorithm. And believe me, to understand this algorithm, you only need some linear algebra knowledge you have learned in the freshman year. Okay, so first we have some observations. Remember that solving a linear BCS over Z2, namely to find a classical solution, this is efficient because we can apply techniques such as Gaussian elimination or by applying the substitution method. The second observation is that the polygroup elements either commute or anti-commute with each other. For example, the x tensor x and z tensor z, they commute with each other, and the single qubit poly operators x and z, they anti-commute with each other. And in the language of group theory, this means that the commutators between polygroup elements are either +1 or -1, depending on whether they commute or anti-commute. And if we want to exchange the order of the product of two poly elements, we simply need to insert a commutator to the formula. Now, the high-level idea is like this. So we first assume this linear BCS has a polystring solution. Then we transform this BCS over the polystring operators into a new linear BCS, which is defined over the commutators between these poly elements. And remember that these commutators take values either +1 or -1. So this linear BCS is defined over Z2, and we can use the classical methods to solve this new linear BCS. If we find such a solution, then we go to the final step, and this later I will show how to assign proper values to the original variables to give a polystring solution. And if by the third step we do not find a solution to the commutator linear BCS, then the underlying assumption is false, and the original linear BCS does not have a polystring solution. So our algorithm solves the linear, give a systematic way to solve linear BCS over the poly group. And this generalizes some previous results, including pioneering work by arXiv in 2012 and a recent work led by Adam Cabello. In their results, they take some further restrictions to the linear BCS. Specifically, that is the number of occurrence of each variable in the BCS. Well, in our algorithm, we do not take such restrictions, and it is the general linear BCS.
Sorry,
Okay.
can I interrupt?
Yes.
I just have a question. So when you transform from the Pauli to the commutator, so this is not necessarily unique, I imagine?
Yes, it is in general not unique.
But it doesn't matter. You just do one transformation, check if it solves that, then whether or not there's a solution, that's enough. You don't need to check all possible ways to transform.
No, we just check one construction.
Okay.
So yes, so this result can check whether this linear BCS has a solution or not, but we do not guarantee this solution is unique.
Yeah. No, it's just that maybe like I was wondering if you transform in the wrong way, maybe you sort of like maybe think that there's no solution, but another way would give you a solution. I guess that would never happen, right?
That never happens, and I will show where this is the case. Okay, thank you. I will now show why this is the case. Okay, so now let's go into the algorithm. So in the first step, we express all the variables through some set of free variables. So this is very similar to solving a classical BCS. Remember that when we solve this, when we try to solve a linear BCS over Z2 to find a classical solution, we can apply for example, the substitution method, and we find a set of free variables. So in this case, remember that the trace of a set of free variables can be somehow arbitrary, but this is always without loss of generality, and this can guarantee you that this procedure does not go into some sumness problem. Okay, so we specify a set of free variables, and we can express all the other variables through these free variables. And that is, we can write other variables as a product of these free variables. And now we can take a similar procedure for solving this BCS over the poly group. And you can also specify a set of free variables and express all the variables through these free variables. And the only difference from the classical case is that since these poly operators may not commute, so they can anti-commute. In this case, there can be some to be determined coefficient in this expression. So these CS, these CI coefficients are due to the commutation properties of the Patti operators. But nevertheless, by this step, the algorithm is efficient, so we can finish the substitution in a polynomial time with respect to the number of variables and constraints. And after the first step, we have a BCS that is defined over this to be determined CS and the free variables AI case. Now we take a further substitution. So we take these other variables back to the original BCS, and then we can transform the BCS into solely these CI coefficients and the commutators between the free variables. So by this step, we just use the polycommutator properties. And as a reminder, K and L are the free variable subscripts, and the CS are the coefficients for other variables. So since this linear BCS is defined solely on +1 and -1, we can solve it as a classical BCS, which finishes in a polynomial number of steps with respect to the BCS size. As an example, I will show how to apply this procedure to the Mermin-Pierre system. So this BCS is given as follows, and you can use substitution method to find a set of free variables, let's say A5, A6, A8, and A9, and express all the other variables through them. Now we take the substitution back to the original BCS, and we can find that this gives a set of constraints over the commutators and the CI coefficients. Well, there is another constraint that is within each original constraint of the BCS, the underlying variables need to commute with each other. So this requirement poses some conditional constraints to the commutator variables. And afterwards, we can solve this classical system and find the +1 and -1 assignments to the commutators and the CS. So this is efficient so far, so forth. Now the problem is we have the assignments to the commutators and this this coefficient CS. We need to transform it back to the original BCS and give the polystring assignments to the original variables. For this part, we have some further observations. In general, for the commutators between operator tensors, so here O is the tensor product of n pi, and O tilde is the tensor product of n pi tilde. Their commutator equals to the tensor product of the composing single qubit operators. Well, if we consider polystring instead, the tensor product is reduced into the product of +1 and -1. So remember that the commutator between the single qubit operators equals to either +1 or -1. And now we have the solution of the commutators, they equal to +1 or -1. Then we can use the single qubit operators to give some assignments. So in the single qubit case, the identity and X or identity and Z operator, they have the commutator +1, and X and Z, they have the commutator -1. So we can simply use these single qubit operators to assign these pi and pi tildes, and these shall give the assignments to the O and O tilde, the original polystring operators. And as a side remark, our assignment was implicitly used by a work by Professor Zhang Fengji in 2013, and we generalized his idea. Okay, now specifically, so in this step, let's say suppose there are p commutators of the free variables, p commutators equal to -1, which are given by ck1l1 through ckplp. Then we can take a p qubit assignment to these observables. So in this assignment, we take the qubit of AI. So AI is a free variable. if I equals to KQ, so KQ is the subscript in these commutators, then we assign the Q's qubit to be sigma X. And if I equals to LQ, then it is assigned with sigma Z. Otherwise, we assign a qubit identity operator to the corresponding qubit. Now, as an example, for the Mermin-Pierre system, we now have this solution for the commutators. And we find that there are 2 -1 commutators, the commutator between A5 and A9 and A6 and A8. So this means that we can find a 2-qubit polystring assignments to the original variables. And using our strategy, we assign the C5, the commutators between the A5 and A9, they correspond to the assignment to the first qubits of A5 and A9, so which correspond to sigma X and sigma Z. And for the commutator between A6 and A8, they correspond to the second qubits of the 2 observables. And here we have sigma X for the second qubit of A6 and sigma Z for the second qubit of A8. And all the other qubits are assigned with the identity operator. Now we have assigned the polystring. We have assigned polystrings to the free variables, and we can use the commutator relation to find the to assign the polystrings to the rest of the variables. And this finishes the algorithm. Okay, and now comes the final part, the outlook. Our work used the linear BCS to construct some quantum pseudo-telepathy games and to find a separation between Clifford NC0 and quantum NC0. And naturally, we think that there are some other ways to construct similar quantum pseudo-telepathy games. And we think this is doable. But if you want to do such construction, you need to prove there is a constant gap between the winning probability of the Clifford strategies and general strategies that require non-Clifford gates. Another thing that I haven't mentioned in this construction, so for the circuit construction, there is some tricky things related with the non-Clifford operations. So the non-Clifford property ruins some statistics, and we need to somehow fix these errors due to the non-Clifford operations. And because of the use of non-Clifford operations, the separation between Clifford NC0 and general quantum NC0 is not so elegant as the separation between the NC0 circuits and Clifford NC0 circuits. And this is we think is very interesting open question for future works. And finally, our result found a decidable problem for the BCS for solving BCS. Well, in general, solving a BCS is an undecidable problem. So we are also interested in finding other decidable results for the topic of BCS. And at last, we hope our work can inspire further explorations in showing the unconditional magic advantage in deeper circuits, and finally prove that BPP is not equal to BQP. And here are some references for our work. And that's all. Thank you.
Okay, thank you very much for a very wonderful talk, Xingjian. So I guess we have a bit of time, yeah, like more than 10 minutes or so for questions. So yeah, if you have any questions, I guess you can just unmute yourself. And if I see you, then I can let you ask your question. Okay, maybe I wanted to ask something first myself. So whenever this linear binary constraint system has no solution, so I mean, so that means like there's no like perfect solution for the Pauli string, right?
Yes.
But is it clear, like, I mean, I can still imagine that there's still an advantage over the Pauli solution over the classical one in some cases, right?
Yeah.
Right. So is it like, would you be able to tell when this happens and when this doesn't happen?
Thank you for the question. I think this is indeed a very interesting question. So our result cannot tell such a difference, but it is true that the polystrings can still provide some advantage. So one instance is the CHSH test. So you can write the CHS test also as a linear BCS, but this linear BCS does not have either a classical solution or a polystring solution. But yet we can show that there is still some quantum advantage.
Okay.
Yes,
Yeah.
but
I mean, I imagine that. Yeah. Maybe it's not so easy to know. Yeah.
yeah,
Okay.
I think the nice thing about the pseudo-telepathy games is that if you are only interested in whether it has a perfect solution, then you can use some group theoretical tools to analyzing this problem. But if it does not have a perfect solution, then the problem is in general very hard, I think.
I agree. Yeah. Makes sense. Yeah. Okay. So yeah, maybe now I should let others ask their questions. Okay. I don't see anyone. I was actually wondering if you were interested in actually showing the construction that you were trying to avoid to mention.
Yes. So here is the construction. So the construction is somehow very complex, and this is the simplest way we found to express our linear BCS construction. So we first have a set of variables, and we can express the variables using an undirected complete graph. So in this graph, each vertex corresponds to one variable of the sort of A. So each vertex corresponds to some A variable, and each edge. So for example, this UV, this edge corresponds to three variables, which we label as X, Y, and Z. And finally, I read two sets of I read yeah I read two edges that are not linked with each other. So for example, the UT and VS, these two edges corresponds to another three variables. So there is one variable B. So for the B variables, the order of the edges is not important. So so for example, the B UT VS is equal to B VS UT. So it does not matter whether you write which edge first. But there is another type of variables. So this UT and VS responds to another C variables, and the order of the edges matter. So we have two C variables for each two edge. Okay, now with these variables, the BCS is given as follows. So there are these constraints. And I think this is the smallest non-trivial BCS. So in order to define sets of edges, you need at least 4 vertices. But for the 4 vertices case, this BCS has a polystring solution. It does not have a classical solution, but it has a polystring solution. And if the number of the vertices is an odd value, then the BCS has a classical solution. Well, if the number of vertices is an even number that is larger than 6, then the BCS does not have a polystring solution, but some general non-cleavable solution.
Okay, I see. Looks complicated, but I mean, I guess like it's sort of like I don't know why it works that way. Yeah. Let me see
Sorry.
if there's other.
Yeah.
Yes. Okay.
Yeah.
Go ahead.
Thank you for the talk. Probably I do not fully understand, but I want to clarify. You in the very first part, you already mentioned there is some advantage for over Clifford circuit and for non-Clifford circuit. How do you need a magic state to come in, but I do not fully understand how you incorporate the magic part. Can you just cap that? Yeah.
You mean how we construct this circuit?
Is this related to? Yeah, this is. I also have question about this part. So how is the randomly you randomly pick them, and how does this help?
Okay. So the circuit construction is as follows. So we can use we can use the I think it is more convenient to describe this computational task by showing how the pseudo-telepathy can achieve this relation problem. So you can imagine that there are consecutive computational sets held by two parts, which we call Alice and Bob. So Alice holds this out-valued computational set. So for example, this part is held by Alice, this is held by Alice, and the even valued computational sets are held by Bob. So Alice and Bob are so the referee, or let's say maybe the one who does the computational task, the experimentalist randomly picks up sets of Alice and Bob and ask the relevant computational sets to give the nonlocal statistics with respect to the input of the nonlocal questions to these sets. So to solve this relation problem, suppose we have a way of doing the pseudo-telepathy, then we can first use so first Alice and Bob can share some some EPR pairs between the consecutive computational sets. So these have bounded fine-in. And now, since assume that this task requires this part of Alice and this part of Bob to generate the detailed statistics, then you need some way to transfer the entanglement to these two computational sets. And for this part, you can apply consecutive well-state measurements and swap the entanglement to the desired computational sets. And since these two sets are entangled, then you can apply the nonlocal. You can apply the measurements in the nonlocal gain to generate the desired computational result. So basically, this is how we transform the quantum pseudo-telepathy game into a relation problem.
Okay, I see. So this is the transformation trick you use. So
yes.
But you mentioned you will random pick the input and output. So where does it come from?
So this is defined by the task itself. So this relation problem requires some random inputs.
I see. Okay. And
so yeah, so this task take random computational sets and take random questions in the local game as the input.
I see. Okay. And so my another question is about how to actually introduce the magic state into your setting.
Okay. Actually, we do not use magic states, but the non-Clifford operations. So these operations are for this part. So you need to use these non-Clifford operations to play the non-local game. For the rest of the part, there is no non-Clifford gate. So we only use it for playing for the last step, play the non-local game between the computational sets.
I see. Thank you.
Okay, thank you.
Okay, so I think we have time maybe for one more question if there's someone has a question. Okay, I guess there's no more questions. So I guess we can sort of end it here. And thank you again for having a very interesting talk.
Okay, thank you.
Yeah. So yeah, I will stop recording now.